So I don't know if anyone had like a chance to see like the problems I posted again, like they're I'm not expecting you necessarily to submit any solutions or anything like that. But at least from time to time, I will refer to some of them like during like our meetings. In fact, I will use one of the problems today, if I have time. But maybe just for fun, did anyone think about the first one? I think that was the one about the matrices that cannot commute. So if you have like, I won't use this anywhere else today, but I thought it could just be fun to discuss it because it's like a short proof if you do it from a certain perspective. So you have two n-by-n matrices, like a finite size. Well, there are different ways to write it, but let's say if the commutator, right, like this is like the commutator of two matrices, AB minus BA, if that's a multiple of the identical matrix, right? For some scalar, for some lambda. So the point that I was telling you like last time is that this cannot really happen unless lambda is zero. Okay, then so there's I mean, again, like it's kind of one of those things that once you see the solution, you say, of course, like this is like obvious, but it's not super obvious if you just like see it stated in that way. And anyone thought about the how to do it, or you didn't? Any ideas of what you could do here? The reason why I was telling you this is important is because later, yeah, probably towards, once I talk about quantum mechanics, then you do have like a version of this, like, which is like the Heisenberg uncertainty principle. Where lambda then it's just like I, the square root of -1 times h bar, which is this one that called the Planck constant, well, over 2 pi. And so in this case, like this relation is supposed to hold, or these two are kind of matrices, but because of this result, then that means this cannot be represented by finite size matrices. So that's why you have to use kind of like infinite size matrices or like operators, which is like the other way we can think about them. But so it's kind of like nice just to connect it because to what comes later, because it just tells you that like in a sense like quantum mechanics has to be infinite dimensional in terms of like the operations that exist. So there's a has everyone seen the trace of a matrix? Okay, so there's a cool trick with the trace of a matrix. So remember, like the trace is just like this the sum of the diagonal elements, or like also the sum of the eigenvalues, right? Then so okay, so sum of eigenvalues, right? So if you take trace on both sides of the equation, then it's almost like for free because then you get that the trace of AB minus BA equals the trace of lambda times the identity. Okay, the trace is linear, so you get the trace of AB minus the trace of BA equals lambda trace of the identity. Okay, we know like the trace of the identity, that's just n, right, for an n-by-n matrix. And then, you know, trace of AB is the same as trace of BA, if you have seen that before. So this actually becomes zero. So that gets zero equals lambda times n, so that forces lambda to be zero, right? So it's like a very elegant proof, right? If you think about it, of course, like how do you think that you have to take trace on both sides? And that's kind of like the like the interesting part. So what tells you like if you want to do like of course there are many things that if you wanted to just try to do like a proof like this in this case like kind of fail. First, like if you want to take the trace on the thing is like this would be now like a identity of matrix of infinite size, so it's kind of like divergent, right? Because you're adding like ones along the diagonal, but there are infinitely many terms along the diagonal. So like the reason why like this kind of is allowed in the infinite dimensional case is that you have to be more careful when you take trace because the trace is not defined for any matrix in when the matrices have infinite number of rows and columns, right? So in fact, they're called like trace class matrices or trace class operators, where those where you can take the trace. So it's like kind of that is what allows these to be kind of like an interesting relation, whereas in here this can only happen when lambda equals 0. So it's kind of, I thought okay, that's like a fun thing to notice, but again, we won't use that for now, but again, yeah, like I think you could ask me about quantum computing and things like that. So I mean, there's still like quantum mechanics, like you can still do some quantum mechanics with finite dimension, finite matrices. It's just that not every feature can be captured with finite matrices. You do need like infinite matrices for certain things. Is that a good question? So okay, so my goal for today was just to tell you a bit about what the Hamilton equations are. I start recording this. Oh, yeah. So last time, like I had started like by telling you what Newton's equations are. That's more like as a motivation. The idea is that if you think about Newton's equations, right? F equals dp dt, or again, there are many ways to write it, or n times a, or n times the second derivative position with respect to time. If you just think about this as an ODE problem, right? Like this is like second order with respect to time. So like a very useful trick in differential equations is just like to introduce like a change of variables, right? To kind of work with everything like in terms of first derivatives with respect to time. In a sense, like that's kind of like how you can think this Hamiltonian equations coming from. So okay, so let's think about our situation. Like if you remember, I have defined the Hamiltonian, but we're working in a very specific case, but again, I'll write this just for notational simplicity. Like I'll just write this like in terms of x and p. So like just imagine again, it's I'll write it in a more general case later on. But just imagine like you have like a particle moving along the x-axis. So it has like a position x, right? And there's like some sort of force like apply on the particle, whatever. So the Hamiltonian just depends on x and p, where p is the momentum, right? So p in this case is like m dx dt. Okay, and then the way I took it to be last time was p squared over 2m plus v of x. And v of x is what you call like the potential energy. So the Hamilton's equations are essentially what you get when you rewrite Newton's law as a system of first order ODEs. So what would that be? So let's start first with dx dt. So what is the XCT? Okay, so that's just, I mean, just if you think about it from this equation, the XCT is just P over M. Okay, so it's almost like a tautology, right? So this is P over M. But then the fun thing is kind of to realize, okay, what is P over M with respect to this equation? That's the, or with respect to this function, I should say, rather. That's the partial derivative of H with respect to P, right? So if you take the partial derivative of H with respect to P, you get P over M, right? So the point is that I'm trying to kind of write like the derivatives with respect to time in terms of like the function H, okay? And so that would be like the first equation, which is almost like a tautology based on the definition of H and P that I gave you. And then the other one, when you turn it into a system of ODEs, first order ODEs, like if you think about it as the variables being X and P, you need also like a formula for the derivative of P with respect to time. Okay, so that's the PDT. So this is almost, if you want to think about it as being just like by definition true, right? So there's not too much content, maybe in the first equation, just almost true by definition. The PDT is kind of more interesting. I mean, you could also think about it by definition from a mathematician perspective, but it's more like because of Newton's law, right? Because of Newton's laws, the PDT is actually F, right? But F, we were working in the case where F was conservative, so that means that it was minus the gradient of the potential function. If you remember that, so F is minus the gradient of the potential function. If you're working in one dimension, that's just like the derivative minus the derivative of B with respect to X. Okay. And then the question is like, again, if I see this here, can I obtain this expression somehow from the expression for H? And basically you can if you take the partial derivative of H with respect to X. So this is, I mean, just think about it. So if you take the derivative of H with respect to X, what happens if you take the derivative of H with respect to X? I mean, this doesn't depend on X, so you just get the derivative of B with respect to X. So to fix it, you will multiply by a negative sign, right? So what I'm trying to say is that like Newton's, what I'm trying to say is that Newton's law, right? Or minus the gradient of B equals M squared, the second derivative of R with respect to T is equivalent, at least, the same will happen when there are more particles. Sorry, when there's more than one variable, but I'll rewrite it in a second. Let me put it like. And then I'll give you the version in terms of like vectors. So it's equivalent to those two equations. So meaning that instead of what I'm trying to say is that instead of solving this equation, you can just try to solve this system of equations and they're like equivalent. Again, because secretly this is just like a definition of like what P is if you just go through what it says. And then this is just like, again, like Newton's, this is like actually like Newton's law, and the other one is just like a definition of P. So it's not, there's really still kind of like one important equation and the other is more like definitional. But the point is that if you write it in this way, what's the nice thing about writing it in this presentation, that is very symmetric in the roles that the variables X and P are taking, right? Because what this is saying is that the derivative with respect to time of X is the partial of H with respect to P, and the derivative of P with respect to time is the partial of H with respect to X times minus one. So except for this minus sign, it's almost like completely symmetric, in the roles of, X and P. Like, it's just saying that you take the derivative of H with respect to, to the other variable. So making sense, question kind of looking better, good. So like, for example, in the case of the harmonic oscillator this spring, so like last time I had written like Hooke's law, if you remember, as P squared over 2M plus V of X, right? So what do Hamilton's equations tell you in this case? Oh, sorry, like and then in the last time for Hooke's law, I had taken like the mass to be 1 and the spring constant to be 1 just to, make it and just to make the solutions look a bit nicer. Right, so here m equals 1 and k equals 1. So what do Hamilton equations look like? I should put like his name here. So these are Hamilton's equations. So what do the equations look like for this particular Hamiltonian? And this is, again, it's called a Hamiltonian in general. And this is having an x, sorry. No, it looks a lot better. So the first equation says that the derivative of x with respect to time is a partial of h with respect to p. That just gives you p. That makes sense. And then, which is, again, it's almost the same as the definition of momentum, except for the fact that I took the mass to be 1. And the derivative of p with respect to t is minus the derivative of h with respect to x. So you get minus x. Okay. So it's essentially, if you put the k, if you put the k again, like it's saying that the force is minus kx, which is what we know from your Hooke equation, how I've written it last time. So it's just, a lot nicer to write it in this way, because it kind of like makes the roles of x and p a lot more symmetric. So there's the biggest advantage of putting it in this notation. In fact, there's a little, as I mentioned, like there's there's some geometry hidden in here if you try to, draw this in the phase space diagram, right? Because let me show you. Let's focus on those 2 equations first. And okay, I don't want to erase this too, but if you look at these 2 equations, like write them in vector notation. So yeah, if you write them in vector notation, that's right. Right, so the phase space is just the first axis is x, the second axis is momentum, right? So you're looking for the derivative with respect to time to be equal to this, to this vector, right? But so what does this mean? Like we're looking like, we're like the solution is going to be a solution is a curve x of t, p of t in phase space. Okay, so the point is like that solving the equations like means like finding x and p as a function of time. So you get like a curve in phase space, right? So what would this be? This is kind of like the tangent vector to the curve, right? It's the time derivative. So it's kind of like the velocity vector of the curve or the tangent vector, right? So like, so this is like our curve, right? So this is the tangent vector, right? Okay, but here, this in particular is telling you that, the tangent vector has to be this vector p minus x. So the question is, what can you say about the vector p minus x? So that vector is like, if you think of this as a vector xp or the point xp, right? Like, what is this vector equal to? That's like a vector that's perpendicular to xp, right? Because what's the dot product between xp and p minus x? Well, that just gives you xp minus px, right? So that's just zero. So that means that this vector is actually perpendicular to the position vector in phase space. So essentially, like the angle should have been, so this should look like a 90-degree angle, which does make sense if you think about it, because like in this case, we already knew the solutions were circles, right? So in the phase space, like that's what we saw last time. So in fact, the curve didn't look like this. Like the curves like look like so like circles. So it's kind of like a cheat, like it's kind of misleading how I'm drawing the curve here, because the actual solutions in this problem were all circles, right? And so for circles, yeah, you do know that the position vector is perpendicular to the velocity vector, right? Maybe I should say tangent vector so that it's not confused with momentum. So for yeah, for a circle, you do know that the position, the radial vector is perpendicular to the tangent vector, right? So from that, just from that fact, you can kind of, if these like equations are saying that the position vector is always perpendicular to the velocity one, you can kind of guess that it should be related to a circle, right? So just like that alone suggests a lot about the solution, even if you don't, if you don't know how to actually solve the ODE, which indicate in this case we knew how to solve them, but I'm just saying that that geometry on its own is gives you like a good hint of what's happening. Is that making sense? So in fact, it's not okay. This kind of picture is not specific to this particular Hamiltonian. So it's kind of more of a general fact from this equation. So let's talk about that. But just to kind of like reiterate, like let me write it. Let me write it in words like explicitly on the board so that this is more clear. So the philosophy of like, this is called Hamiltonian mechanics, by the way. So the philosophy, like from this point of view, is like you forget about forces, like no, you no longer care about them. So there are no forces if you prefer to think about it in that way. So no more forces. You just have like this function x, this function h of x and p, right? So you only have the Hamiltonian, which is a real value function. Defined in phase space. And you study the solutions to Hamilton's equations there. So again, for today, I kind of want to focus in the case where like it really just depends on x and p, because that way we can just do everything with 2 by 2 matrices. There's everything is very concrete. It's kind of like nice to know this what's going on in this case very well. And then you'll see the generalization to the general case is essentially the same, just like put vector notations everywhere. So like philosophically, everything, it's kind of like the same with linear algebra. If you understand really well 2 by 2 matrices, you kind of understand linear algebra, and then the rest is just like you know, a lot more tedious in terms of the computations, but like really the main features already happen in 2 by 2 matrices. So, and then you try to solve these things. Okay, so here's, let me see if I want to go in this order. Kind of all over the place with respect to my notes. Yeah, but. Okay, so again, I'll leave something like a diagram here of what the phase space is like. So again, this is going to be a curve, right? Like the solution is going to be x of t, p of t, so you get like a curve, the solution curve. So let's call this x of t, p of t. So this is like a particular solution to Hamilton's equations. Of course, I'm putting a lot of things under the rock where you have to assume, okay, the function is nice enough for h so that, the uniqueness theorems of ODEs apply, blah, 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 blah. It's like, that's like not like a very, like, different thing from what, you usually would ask like in a ODEs class. So usually you do want like, uniqueness of solutions after you specify, maybe I should say that. So you want, if H is nice enough, H is nice enough, there's a unique solution. There is a unique solution. Given like, initial conditions, like, like the initial position and the initial momentum. Which is what you would expect for something that secretly was a second order ODE, right? I mean, in terms of like Newton's equation, so you needed two initial conditions, or here because it's like a system of two first order ODEs. Okay, so this is like the solution curve, right? And the XCT is like, like a tangent vector to the solution curve. So this is like a tangent vector to the curve. So what do the equations say? Okay, so the equations, like, let's just play with these for a moment. I'm just going to rewrite them here first. So that's okay. I'm using vector notation, and then it takes some like a trick to kind of realize, oh, you can actually write this as the following. Okay, so it's kind of useful to convince yourself by just doing the actual product, right? If you do the multiplication of this matrix with this vector, you get the HDP, which is here, right? And if you do the multiplication of this row with this vector, you get minus the HDX, right? Why is it nice to write it this way? Because if you write it this way, what is this? It's just the gradient of the vector of the function h, right? In terms of like the coordinates x and p. So you could write this like the gradient of h. I'll just emphasize that I'm taking the gradient with respect to x and p. So I'll just like, which is just because later on we'll have different coordinates. So it can be like a mess if you don't know what you are taking the gradient with respect to. So let me just put here x and p. Okay. And then these matrix, I don't know if you remember, like it showed up last time. It's like what I'm going to be calling the matrix J. Okay, so J, and this is like kind of like the fundament. It's kind of like the most important matrices in all of these like discussions that we'll be having like during the seminar. Like this matrix H is J. Like it's really, really important. So it's like this name is kind of reserved for this matrix, like so it's like a super important matrix. The matrix. And I don't know if you remember that I mentioned this last time. It's one of the nice things it has is that it squares to negative the identity, right? So actually, and it's in fact like if you remember like the general formula for a rotation matrix is that rotation by 90 degrees clockwise. So this is kind of like a 90-degree rotation, clockwise rotation. So it's in a sense like, it is a version of the number I, right? Like square root of -1, but it's kind of like the matrix version of I. So what this is saying is that, if you think of the gradient as a vector field on the phase space, right? The tangent vector is a 90-degree rotation of the gradient. So you take the gradient, so in this picture, that means that the gradient had to go like somewhere like this, right? The gradient was something like this, and then you multiply it by j to rotate it by 90 degrees, and that gives you the direction of the curve. Okay, so so the point is that like a solution to the equations is such that it evolves moving perpendicular to the gradient. Okay, so like so the solution curve, right? So the solution curve is such that this tangent vector remains perpendicular to the gradient of h. Is there any questions about this? So that's already like a very nice geometric picture of like how the solutions look like on the phase space. Okay, there's something more to say. So this is like this thing is just as a bit more extra notation. Let me put like Hamilton's equations somewhere in here so that I can refer to them at any moment. Otherwise, it will be kind of a, I know. So this vector j times the gradient is called the Hamiltonian vector field. Okay, so these so the Hamiltonian vector field is defined as so let me just call it v sub h for the particular Hamiltonian function that you're using. So it's just like j times the gradient of h. Okay. So if you kind of, it does make sense to, if you want to write this in a more like simplified notation, because it's, you can write like z of t equals like x of t, p of t. That makes sense because again, like in a sense, there's some complex stuff going on just because this is kind of like the square root of -1. And it's like, essentially what you would do if you had called just this y instead of x, instead of p. So like, if you do it that way, then you can rewrite them. You can rewrite. And just to emphasize that this I'm taking as a vector, I'll put like an arrow if you want. Rewrite the equations as. Maybe this looks a lot more simple, So you're saying like that you're looking for some curves whose tangent vector is like given by this Hamiltonian vector field. So what are these called? What's it called? What's the naming notice for like the curves to a vector field? It's on my tongue. The integral lines or something similar like this word is called. Yeah, the integral curves, right? So these are like integral curves. So for like the Hamiltonian vector field. Okay. So far, does that make sense? Questions?
Yeah. So is this where the idea of energy being conserved comes in? Because if the if d if dz dt is perpendicular to the gradient times in the gradient, or then h isn't actually changing in value.
So let's see, so if, okay, so yeah, like it would be, right, yeah, so this is like this, top three thing, right? Like if you have this curve that's perpendicular to the gradient, it's like a level curve, right, for h, yeah, so in this case, like h would be conserved along the level curve, correct? Yes, good observation. Like there, again, like there's kind of like more like general ways to set up everything in this context, but so like, like for example, for up, because again, my goal is just to kind of have like 2 or 3 examples that we understand really well, and then we can just do like a quantum mechanics version of it, right? So it's not like kind of like a dissertation on like all the possible variations of this method, but like, so for us, like it really is enough, that H, I'm always thinking of H as something like this, but of course you can do more general versions for this H. So H really can be more like a real value function that doesn't have to take this particular form, etc., etc. But yeah, like the nice thing about taking it about in this way, it's just like everything is very explicit. But like yeah, what you're saying is, once you have like the equations, in this way, like not just like for this particular H, but just ignoring this H, then yeah, it's a consequence that since it's perpendicular to the gradient, then it does, you know, it is a level curve, and that is and then H is conserved, and that's regardless of right H. You just need obviously to H is sufficiently smooth so you can take derivatives, but except for that, there's not really else being used, right? There are like situations where H is allowed to depend explicitly on time, so that's a little bit more tricky because then the gradient is changing on time. But like yeah, in this case, it's everything like fine. It only depends on XMP, so it's okay what we're saying. Cool. Anyone else? And then there's the other. Okay, so this this is the first. And again, this is not like the real physical space, right? Because the phase space is like the positions, say, of the particle together with its momentum. So it's not really what you would see anywhere. It's that the geometry is like more clear somehow from this perspective. So another thing that happens is that this vector is solenoidal. Okay, so let's just think about okay, like I don't need this anymore. So here's another cute fact about this vector field. So again, you can think about this being a vector field on all phase space, right? Because you take the gradient, there's a vector field, and then you just rotate the gradient at every point by 90 degrees clockwise. Okay, so that gives you a vector field in phase space. So here's another fact. This vector, the vector. I don't know if I don't know if this is like a standard terminology that you have seen. Like, do you know like the definition of solenoidal vector field? So that's something that is here taught necessarily in multivariable calculus, but it just means divergence free. Okay, but this is like kind of like so divergence free is also called like incompressible if you think about it like it's in fluid dynamics. So it's called divergence free. Okay, so maybe it's actually that this like on its own is like maybe easier to understand what it means. It just means that the divergence of this vector field is 0, right? So what the divergence this V of H, well, like the V of H, like the if you're taking the divergence of Right, and I'm going to think about the divergence, like, I'm using the notation a little bit, it's just this. I kind of feel a little bit weird writing everything as a column vector, but I just want to be consistent. It does look a bit ugly this way. Right, and then it just vanishes because of the commutativity of the mixed partial derivatives, because again, like, we were living, like, as in any reasonable situation, we're assuming the H is nice enough, so that, otherwise, there's not really much you can do. The possibility, does that make sense? So why is a divergence-free vector field useful? Okay, so there's like two perspectives that you can take on to know why this is nice. So why is this so oh, maybe, yeah, do you remember in the fundamental vector theorems of vector calculus at the end of multivariable, they're like the two important ones, and the divergence was related to the flux, right? And then the curl was related to the, the like, the work or like the circulation. But so here's like one way to think about this. Okay, so imagine that you draw a blob in phase space. So what do I mean by that? It just means like, okay, maybe, and this is kind of like the more like an approach that you would take in statistical mechanics or probability theory, where it's like, well, maybe you don't really know quite well the exact initial position and initial momentum of the particle, right? So maybe like, the initial position and momentum of the particle is like within certain margins of error, right? So you get like, it's kind of like the initial position and momentum is kind of like in some region of phase space, right? But it's not like you don't necessarily know that point like with the exact accuracy. So it just lies somewhere in this blob, right? So let's call it like region R. Okay, R0, because that's where like, I know the initial position and momentum lies. Okay, so if you wanted to do this more formally, you could put like a probability density function, like that kind of tells you the probability that the particle had like an initial position and momentum. But like the evolution is deterministic. So even if you don't know what the initial position and momentum is, like everything is like deterministic. So if you start the system with the initial position momentum somewhere here, like you kind of get some curves emanating from this blob, right? So let's just draw a bunch of curves here. And maybe the blob gets deformed as time goes by. So the blob becomes blob at time t, right? Is that okay? And then, so this is kind of like, okay, if I get started my system at this position momentum, then at time t, my system is somewhere here, right? So the question is like, you could compare, for example, the areas, what's the area of R of t versus the area of R0? Or like, if you do this like with more variables involved, it's like what you would call like the measure, like the Lebesgue measure, like or the volume, like hypervolume of the regions. And the thing is, the fact that the vector, these curves are evolving, so that the tangent vector is Hamiltonian vector field, which is divergence free. And so the fact that this vector is, divergence free means that the area is preserved. So like the area doesn't change over time. This is called like the Liouville theorem. And I'll probably add like on the problems, like more detailed, like a problem with more details if you want to fill in, see why this works this way. But so the Liouville theorem says that, if you have like a region, if you have a region R naught in phase space, and you evolve it under time following the Hamilton's equations, then the area is preserved. You evolve it under the Hamilton, using the vector, like, the vector field, in the Hamiltonian vector field. Then, the area of, then for any t, the area of R of t is the same as the area of R naught. So what this means is that, again, if you take a blob, some region, again, sufficiently nice. If you take a region in phase space and you evolve it using Hamilton's equations, then like the area is preserved. So you can kind of, maybe you can stretch it, you can squeeze it, but no matter how you deform it, like, the area must be before and after the same. Yeah.
Do these blobs in space represent anything, or is it just general collections of points?
No. So it's kind of like, it is better to kind of take like more of a probabilistic interpretation here. So it's like, you can still think that you're just talking about a single particle, right? Like, so for example, in the spring problem, like it can be that, like maybe show here. So in the spring problem, it can be that, you're still keeping track of the position and the momentum of a single particle, right? Like the one that's attached to the spring. But now maybe you're like saying, well, I'm not 100% sure what was the initial position or velocity of the spring, of the particle. So there's some sort of uncertainty if you want to think about it like way.
So it's like a collection of possible
Correct. It's kind of like a collection of possible,
positions and momentum.
positions and momentum. And then you are like, which is a kind of more like an experimental perspective to it, right? Like, and then you are like, well, since I still know that the evolution is deterministic, even if I don't know the initial conditions precisely. And then you're just asking how that possibility space, evolves. That is like mathematically equivalent to what's called like an ensemble. I don't know if you have seen the terminology before, but an ensemble is kind of like similar to what you're saying. Maybe, let's put like a bunch of virtual particles, each with like a position and momentum in this blob, right? And so it kind of like you put like a bunch of clones and see them how they all evolve. But so it's kind of more up to you whether you want to think about it as a single particle just with uncertainty in position of momentum, or just like an infinite collection of particles, which precisely the momentum and position, but then like just kind of all coalesce in a certain region of phase space, right?
Mhm.
So, and that's kind of like, again, that's like more of the perspective like that you take in statistical mechanics, because in statistical mechanics, because here everything that I'm describing is kind of like for a single particle so far. But if you want to describe like a gas, if you want to describe a gas, we're talking about 10 to the 24 Avogadro. Like it's kind of like an absurd number of particles, right? It's 10 to the 23, 10 to the 25 or something like that particles. So you cannot pretend like in any reasonable way that you would know like the positions and the momentum of all of them, right? So you have to introduce probabilistic methods at some point there, like for anything realistic to be obtained. And then like this is kind of like this picture interacts nicely there, because then you're like, oh, you're keeping track of like, the positions and momentums of all these particles, but within certain uncertainties, because like you cannot expect again that you will know them all precisely. And so the fact that the measure is preserved, like, does have like consequences when, say, like, you want to find the equilibrium distribution, like the one where, like, like, or the most likely configuration of the gas and things like that. So it's kind of like no, like, that's like the fun part. But yeah, like, think about it like a space of possibility, like, possible momentum, positions and momenta. But yeah, the thing here is like, it's like yeah, what makes this useful is that it interacts nicely then with other things, because, like, in a sense, the area being the same is kind of like saying that there's like a conservation of probability taking place. So or like there's a, if you thought about this being populated by literally actual particles, then like you're not creating nor destroying particles through time evolution. So like it's kind of like they are all going somewhere. So you can still keep track of everything. Yeah.
Can we say anything about how the heightened width of the blob changes over time? No.
Oh, right. So there's actually so for 2 dimensions, like, it is really like like, okay, so in 2 dimensions, it's really what you would call like an area preserving diffeomorphism, where, like, there's not too much you can say, but there's like, I mean, once you introduce more variables, there is something like, I'll talk about that later in the course, because this is actually one of the most important results, which is called the Gromov non-squeezing theorem. So there's like this, like, it's kind of, I don't know, there's like a famous quote in the Bible that, it's easier for like the camel, like, it's easier
Going through the eye of the needle.
than
We're
a,
trying to enter heaven.
right, like, so there's like, yeah, so the no squeezing theorem, like, every time people mention it, I'll bring the correct quote that time, but the no squeezing theorem says actually that while the area has to be preserved, like, you cannot squeeze things too much in a technical sense of the word. Like, yeah. But like, really, to see that precisely, we do need that, like once you have more like sorry, I should have said this, like, once you have more degrees of freedoms, means once the phase space has more dimension than 2, because I think 2 is like just like not much that you can say, but once like the dimension. Oh, these things are always even dimensional, so like you can skip 3, so it's greater or equal to 4. Then yeah, these things, like, obviously here you wouldn't talk about area, you would talk about hypervolume or Lebesgue measure if you want. Then these things cannot be squeezed too much in a precise sense. The area still needs to be preserved, like hypervolume still needs to be preserved, but yeah, you cannot do like just like something completely crazy where you just like do whatever you want as long as you're preserving the area continuously, let's say. Or then there are more restrictions besides just preserving, the area. They're like, then the region R of T can be squeezed too much in a precise way. So one of I hope I'm not saying it the wrong way. It's like, for example, you could have like a ball, like the analog of a ball in phase space, a certain radius, and then you cannot squeeze that into, like, say, a cylinder of a smaller radius. That things of that sort, which kind of like doesn't mean maybe too much for you if you just say it that way, but it is related to something that's called symplectic capacities, which is very useful these days, like for research purposes. I mean, like, and then it's also, you can think about it like another way of saying it is like, if you had like a ball and you project it to planes, like like you are like in a higher dimensional space, so you can project it to planes of X and P, then the projection cannot be like a above smaller radius. So like the radius, like it's kind of like you cannot contract it in certain directions. Like the thing is like to make this more precise, we do need to talk about conjugate variables, which I still haven't told you about. So it's just that there are certain directions, there are certain planes that you cannot contract it too much. There are other planes that you can like in terms of like the projection. But for that, yeah, we still need a little bit more terminology, but yeah, it's a good question because it's not, and this is kind of like very written like in the 80s, I think, when Gromov proved all these things. Which by mathematical standards, it's kind of like more like new stuff, because Hamiltonian mechanics in a sense started with Hamilton, like, I don't know what, like 18th century, like, so many things were, or 19th century, probably. So many things were like kind of known then, but like this property about the non-squeezing is like more modern by most standards, if you have like a result from the 80s, that means that you have to update your textbook. You're gonna use like the textbook that people were using in the 50s or 40s. No, that's like a fun part as well. Okay, so okay, making, yeah.
Does RFT have to be like one connected region?
No, I mean, you can like, you could like that, for simplicity, you could like, I'm not assuming it that way, but yeah, like you don't have to imagine that, it had to be, connected, but, well, you have to think, so I suppose like if you started with something I mean, I guess if you started with something connected, there, like depending on the system, there could be, I think I would have to think about whether you can have like a, it can become disconnected or not. I would say, I mean, maybe it could happen that you can, like, again, like, if you don't know anything else, maybe, yeah, it can shrink, like, one region could shrink to like a point or something like that. But for now, like, for now, think about it as being connected, but yeah, topologically, if that's kind of where you're going at, like, yeah, it's not that like topological properties would need to be preserved per se. So like, I suppose like you could change from simply connected to just being connected or things of that sort. But I mean, that is like an interesting question where you do have to get, I guess, into the specifics of like the Hamiltonian, like how much the topology changes. Because for example, in the spring problem, really the evolution is just rotating everything counterclockwise. So like, there, when it's like the evolution is just rotation because everything is kind of circles, then yeah, there's not much anything interesting that will happen, right? Because like you started with the region and then yeah, you just rotated counterclockwise. But then yeah, there would be more like there would be more interesting situations, and then like you do have to be careful with how you set up things. Because like, for example, let's actually, as a segue, not that I wanted to get like into this, but it could be fun like to discuss it. Like, the devil is in the details for all these things. So for example, there's like to check if someone wants to read more about it, like I can tell you I could give you more details, more literature. But say like one like cute problem, like an generalization of the problem with the spring is kind of having two springs. Okay, that makes sense. So, or like just or let's say two masses. So you have like a mass connected to a rigid bar. So like this is like mass one. So maybe like, let's just put this as the ceiling, like think of this as the ceiling. So from hanging from the ceiling, you have like a rigid bar, and then there's a mass connected to that one, right? So it's rigid, so like the length of this, like this segment doesn't change. And then, so this is map one. And then you have like an attached to this mass, there's another bar, and then you have like another mass connected to this one, right? So you have like two bars here. And then you can be like, okay, describe the evolution of this system. So for example, one of the things that you have to think first is like what coordinates you want to use to describe the system, right? So two coordinates that kind of make sense to describe the system, like say, like if you draw like a vertical line where like this first bar is attached, then you can use an angle theta with respect to the vertical line, and then another, you can draw like a parallel copy of the vertical line here. and then you can draw another angle theta, right? So you could just, like, once since the lengths are fixed, once you know theta one and theta two, you can describe where all the particles are on the plane. So if you think about it in terms of like the like, the position coordinates in this case are theta one and theta two. And so the topology of that itself is just like the donut, right? Like the torus, if you have seen this, right? Because so theta one, theta two. Right? So in this, and then the phase space like has like two more variables because each of these coordinates has like its own momentum. So I can tell you more that how it works once we have a little bit more theory. But if you say that the the configuration, like this is kind of like a torus, like you have to make decisions on whether you want to include like silly situations. Like for example, what's a silly situation where this bar is completely vertical, right? So when this bar is completely vertical, do you want to allow like a situation where like you rotate it this way 180 degrees? Because if you allow that, then you kind of like, there can be like a small collision between the two bars and things of that sort. So there is some thinking to be made about how realistic you want the model to be, or whether you just throw certain things like ignore certain small details like that. So like at least it's definitely a subset of the torus, right? But like, yeah, there could be like extreme exceptional configurations where you don't want maybe necessarily to think of them as physically possible, right? So a lot of like these questions about whether there's topology change in the regions depend a lot on how careful you want to be about defining like all the values that the things can take. For example, another version of that would be, if you have like if you have a mass, well, say if you have, oh yeah, like for example, if you have like two masses like on the plane, right? On the real line, each of them would have its own coordinate, right? So just in terms of coordinates, that's kind of like, an R2, like again, each of them would have its own momentum. So that would actually be 4 in total for the phase space. But like maybe you don't want to literally consider the situation where like they're on top of one another, which is when x1 equals x2. So maybe you want to eliminate the diagonal from this space because you don't want like collisions. Or like if you want collisions, you have to do something different. Like, you have to be a bit more tricky, because then like kind of like the trajectories would pass through literally next on top of one another, and then like their uniqueness of the ODE kind of like is messed up a little bit. So all of these are, yeah, subtle points, but in general, I think, yeah, if I have to make a guess, yeah, I think the topology can be changed, but it depends a lot on like, how you set everything up to see whether that works or not. Okay. Oh, so I have so I have just a few minutes left. So let me just finish with a motivation for what we're going to do next time. So the point next time is that we want to describe why is it related? I still haven't told you too much about symplectic linear algebra, which is where we're headed, and that will appear next time. So. Well, just as a warm-up, if you remember again, I will keep going back to this a lot of the time for this seminar. So if you remember, this was a Hamiltonian for the spring, right? So we know, I had written this before, right? Like we know this is how, oops, I still keep writing here when I should write just X. We know that these are the Hamilton's equations for this particular spring, right? But then what you could want to do is do a change of variables. That's a very common thing that you do multivariable calculus when you doing integrations and other things. So once like a natural change of variables that you could do here you could do like a change of variables like to polar coordinates, right? That kind of makes sense. And I will use kind of like the notation of polar coordinates, although later on, like we do want to use like a more like regular notation. So, but for now, I'll just use like the polar coordinate notation. So polar coordinates, like, what would you write? Like r equals root of x squared plus y squared, well, what plus y squared, but now it's p squared, right? Because p is kind of like working as y. And then you would do theta equals b r tangent of y over x, but it's p over x in this case, right? Okay. So this is actually was in one of the problems I wrote for you in the PDF. I don't know if anyone had like a chance to read it, but since if you have like a solution to the equations, then x and p depend on time, right? So for a solution of the equations, r and t and theta would be functions of time, right? Just because x and p are functions of time as well. But in this particular case, it's kind of easy to know what the time derivatives are. So if this one should be the fastest. So what is the time derivative of the position in this case? Let's see. Well, it's just zero because we're moving on circles, right? Like solutions are circles. So there's no, R remains fixed, right? If you remember, for a particular curve, for a fixed curve, we're moving on circles because h is constant, and this is kind of like, if I'll actually get to that in a moment. So like there's not much to check here, like R is constant. Okay. And theta, that one is a little bit more tedious, but if you use some intuition, it's easier to figure out the answer because theta is like how fast the system is rotating, right? And I chose all the coordinates so that it was rotating at omega equals 1, like the frequency and it's like a clockwise rotation. So like it should just be -1 because like everything was normalized so that like the frequency of rotation was 1. So the derivative of theta with respect to t is -1. So you kind of can guess that from like the geometry, like the solution of the geometric problem. Now, what's the fun part here? And this is where I want to get at, that if someone had said, oh, let's rewrite h in terms of like these new variables, right? That's a very natural thing to do. So if you rewrite h in terms of the new variables, what do you get? P squared plus x squared is kind of like r squared, right? So you just get r squared over 2, right? So this is how h looks in polar coordinates. And then you could ask, oh, like maybe you don't know, you could say, can I get these time derivatives from the Hamiltonian written in terms of h, right? So because the point is like once you have the Hamiltonian, like the idea is that the time derivative should be found can be found from the Hamiltonian. So if you just like try to kind of use the same equations like in the polar coordinate system, what do you get? Like now the variables are r and theta. So let me just emphasize that here. Although theta kind of disappeared like in this case because of the symmetry, but that's okay. So if you maybe you think, well, and this is also not super clear. If you write r and theta, which one is working as x and which one is working as p? Is something we also have to figure out. It's a little bit more subtle than that. But let's just because I wrote it in this order, let's just think that h is r is like x. So you should say, well, the derivative of r with respect to t should be the partial derivative of h with respect to the other variable. So you ask, oh, is this like the derivative of h with respect to theta? And yes, it is okay. This one does work, right? Because you just get 0 here. Which does match like what we kind of knew because of like we understood the solutions. But then if you do like the same with the other variable, right? If you take the derivative of theta with respect to t, right? If you do that with respect to t, the question is that going to be the minus the derivative of h with respect to r, right? But the derivative of h with respect to r is minus r, right? Oh, there's a minus here, so like this just gets you -r. So you don't get -1, right? So this, what this is saying is that if you use this change of variables, you cannot reapply the Hamilton's equations. If you just like try to naively apply Hamilton's equations, you get the wrong answers for how the solutions look like. So that would lead us next time to talk about a canonical transformation. So a canonical transformation will be a change of variables where you can still apply Hamilton's equations without like any thought whatsoever. So like, where like literally everything, what I'm trying to say is that, if in terms of like new variables, you would still have the derivative of x prime with respect to t is like the partial of h with respect to p prime. And the derivative of p prime with respect to t is minus the partial of h with respect to x prime. So these did not happen for r and theta, but there are changes of variables where literally you can just like find the correct solutions by applying like Hamilton's equations in a naive way. And so once you do that, you'll see these Hamiltonian transformations are equivalent to what's called symplectomorphism, which means preserving a symplectic form. So that's how we get into the topic of linear algebra and symplectic linear algebra. So that's like a key thing to do, but I'll discuss it next time because like it takes some calculations. So maybe I think we should end the sentence a bit early, but let's take here. Yeah.
Here, it's only off by a constant factor, since r is constant, right?
Right, but that's still enough to, yes, that's a good point, but yeah, it's still enough to kind of screw it up. Like, maybe since I have time, this is like, here's one that's actually on the nose, perfect, so a perfect change of variables. So instead of like r, like I'll keep theta. I'll keep theta as the same as before, right? But I'll use I just as, let's see, do I need it? Is it x squared plus? Is it with 2? I think so. Oh yeah, let's just put it's okay. So it's almost like it's just squaring the polar like r squared, right? So what does the Hamiltonian become in this case in terms of like I and theta? It just becomes I, right? So if you take the derivative of I with respect to time, this should be like the derivative of h with respect to theta, which is still 0, good. And then the derivative of theta with respect to time. Now it is the derivative minus the derivative of h with respect to I, which is -1. So this is actually an appropriate change of variables. And actually, this is what is called like action angle variables in this case. That doesn't matter too much. But the point is that this one is allowed, whereas the other is not. One of the things that happens, this will be more clear next time, is that you do want if you remember, the Hamiltonian vector field was divergence free, so that the areas were preserved. So whatever change of variables you do, you want to change of variables whose Jacobian is 1, because you want to preserve the area, among other things. That's not the only condition, but like, it's a necessary condition. So, but like this on the nose agrees. Like, so this is like an allowed change of variables. And so what I'm trying to say is that going from x t to I theta is what we would call like a canonical transformation in their terminology, whereas this one failed by a bit, but it just fails. So, but here, like, even when you look at this, it's like, wow, it's not super obvious which one had to be like momentum and chord and which one position. So the point of like the formalism is that it's general enough so that you can kind of drop those interpretations, but it's still, once we talk about Poisson brackets and other things, we can be a bit more precise about which is kind of like position and which one is momentum. And then that's also related. There's like some, I don't know, has everyone taken group theory? Well, I mean, there's some group theory involved. Linear algebra, so again, I'll put some things of that sort like on the problems if someone wants to dig a bit deeper. But yeah, like one of the things that will be important is that the Jacobian of the transformation has to be of determinant 1, so that it preserves like the areas. Okay, so yeah, no, but thanks for your question. Like, no, maybe it was good to say it today. So let's end here, and yeah, we can chat if you like. If someone wants to ask me something else, we can keep chatting. But if not, I think this is a